All right, let's go ahead and get started. So starting chapter 4 today. Any questions about anything before we jump back into things? All right. So chapter 4 is about gonna talk more about like the structure of these things called matrices and vector spaces. So to get started, let's kind of set the stage a little bit. So talk about these two different things that maybe they're not all that different, but vectors and matrices. How are vectors similar to matrices? Or how are they different, depending on which way you want to come at this? Go ahead. Which one? Which one are you talking about? They both do that. Okay, so that's probably the biggest way in which they're similar. What's the? Are there big differences between the two? Vector's one dimensional, right? So probably the biggest difference. So um, when we think about a matrix, it can be, it can have any number of rows and columns. So let's say that, we have a 3 by 3 matrix here. But we can also say that this thing has, 3 column vectors in it. So what kinds of things can we do with vectors? So what things have we done so far with them? Multiplication. And when you say multiplication, what do you mean by that specifically? So let me write down a vector. 1, 2, 3. What's something we can multiply that by? Okay. So we can multiply it by a row vector. So that's something that's absolutely legal to do. Does this product actually exist? I think so. What other kinds of multiplication can we do with vectors? Scalar. So I can multiply a vector by a scalar, and that basically multiplies every entry in that vector by a scalar. So we can do multiplication in a couple different ways. How else can we operate on a vector? Go ahead. What's that? You can add them together, provided that what's true. What about the dimensions? Got it. So they have to have the same order, same dimensions. And if they do, how do you add them? Yeah, entry by entry. So 5, 7. So we got vector multiplication, scalar multiplication, vector addition. Is there anything else we've done, or is that about it? I mean, we do a lot of combinations of things with them. Like if we think back to like our row operations, we can add multiples of one vector to another vector, but that really, we're just kind of condensing a bunch of these operations together. But really, these are the things we can do. Kind of answer that question. So let's talk about some definitions before we jump into the things I need to use them for. So this symbol here, like this blackboard R, this puffy R, that stands for basically the real numbers. So if you see that superscript n, that's basically a number of dimensions. So Rn is a set of vectors with exactly n entries. So few examples and one counterexample here. 1, 2 is a member of R2. Is this a symbol you've seen before, like that pitchfork looking thing? So what this symbol basically means, I'll be using it a little bit more from now on, is what this really says is an element of. So the thing on the left of it is an element of this set on the right. So basically it shows membership. So 1, 2 is an element of R2 because 1, 2 is a vector that has 2 entries in it. 1, 2, 3 is a vector that has 3 entries in it. 1, 2, 3 is not a member of R2. So we get on the new symbol, new vocab. Okay. Or is it new to you? No. I've seen some no's, some yeses. Okay. So a vector space is not something we talked about yet. So what's a vector space? A vector space is a set of vectors that has all the following properties. So I know it looks like a lot, but let's kind of take them one by one. So number one there. So we're assuming that U, V, and W are just generic vectors, and R and S are arbitrary real numbers. So basically, if I take two vectors U and V and I add them together, then I'll get something else in that space. So go ahead. Big S is a set. So in this case, I'm calling S my vector space. So when I say a set, like that is like, that's just a group of things. There is no requirements for that. That's just, it's a collection of objects. They don't have to be united in any kind of way. But now that I'm calling it a vector space, now I'm saying it's a set with these very specific conditions. So I'll give some terms to some of these because I don't think we want to write all these symbols down every time I want to talk about them. For this first one, I'm going to say closure. And what I mean by that is it's closed under addition and closed under multiplication, meaning that if U and V are in my vector space, then if I add those together, I get another vector that's already in my vector space. Or if I multiply one of my vectors by a real number, I get something else that's already in that set. So another way to say that is I can't add two things in my set together and get something that's not there. I can't add my way out of it. This is kind of as an informal way to say that. If I add two vectors together, does number 2 surprise anybody? Or does that kind of act the way that numbers act in your head? So this is this property called commutativity. I can move things around. Number 3 basically says that if I have 3 vectors I'm going to add together, it doesn't matter which 2 I decide to add together first. We call that associativity, meaning I can take them pairwise in any order I want. So I'm not going to go through all 9 of these like one by one, just to say that a lot of the things about vector spaces, these are things a lot of these things we take for granted with real numbers as well. If I add a 0 vector to a vector, what do I get back? Whatever I added to the 0 vector. It should have no effect. If I multiply 1 by a vector, what should I get? Whatever that vector is. So hopefully that acts the way we expect 0 and 1 to act with real numbers. So all that to say, hopefully a vector space contains all these things that behave in the way you'd want them to, in the way you would expect them to. So any questions on that so far? So hopefully so far I am just giving formal language to things that we already kind of expect. So what is a subspace? Actually, we're not there yet. What's a subset? So if I have 2 subsets, A and B, A is a subset of B if everything that lives in A also lives in B. So if I draw a diagram here, if this is what A looks like, and I'm telling you that A is a subset of B, what does B have to look like? It just, as long as A is totally contained inside B, then that's what I'm talking about. Is A a subset of B here? Seem doubtful. Are there things that are in A that are also in B with this thing here? Are there things that are in A that are not in B? Then the answer is no, not subset. So in here, A is a subset of B. Over here, A is not a subset of B. New symbol for you. Maybe. So yeah, this symbol that I put between A and B, that says the thing on the left is a subset of the thing on the right. The thing on the left is fully contained inside the thing on the right. So that's only true if every single element that lives inside A also lives inside B. If you have any exceptions, if there's any one thing in A that's not also in B, you don't have that subset relationship. How are we doing on that? Okay, if we're good on those two things, then what's a subspace? It is a combination of vector space and a subset. So basically a subspace is a thing that's a vector space on its own, but it's also a subset of some other larger vector space. So right now I'm throwing a lot of like generalities at you. I'm asking you to bear with me before we get into the specifics, where I hope this becomes more concrete. So any questions about all the new terminology yet? Okay. So this section is called the subspace test in the textbook. Basically, how do you know if a set of things you're looking at is an actual subspace? Here's the way we check. You have to meet these two conditions. And I think I gave the same name to both of these on an earlier slide. So basically, if you have two vectors in a vector space and you add them together, that result also has to be inside that set. So this is called closure, and specifically closure under addition. So this one is called closure under multiplication. So another way to think about both these conditions, if I have a set of vectors, then I should be able to add any of those vectors together in any way I want to and still get something else that's already in there. Or I should be able to multiply those vectors by any real number I want and still get something that's already in there. If I fail either one of those, I don't have a subspace. How are we feeling? All right. Let's look at some things and let's talk about it through subspaces. So this thing S right here only has one vector in it, the 0 vector. Is that a subspace? So let's think about what the two conditions are. So what's condition one? What about addition? I mean, I can always add, but what's special about if I add things together? Okay, so what kind of things are in this subspace? There's only one vector in here. And let me do this. Let's cross off n here. Let's say that it's 3, just so it's easier to think about. The only vector that lives in here is this. So if I want to add things together, the only choice I have is to add it to itself, right? If I add it to itself, what do I get? 0, 0, 0. So is this closed under addition? Is there any way for me to add the things that are in this to each other and get something that's not already in there? I'm only going to get the 0 vector back. So that's condition 1. What's condition 2? Go ahead. Scalar multiplication. So let's take some k. Choose any value of k you want. What will this result be? Yep. You're just going to get the 0 vector back, right? And that's true for no matter what real number I set k equal to. So do we have closure under multiplication? So is this a subspace? Yes. And you might hear this called the trivial subspace because it's the smallest subspace that can exist. It only has that one vector in it, but it still meets all the conditions. Questions on why that one passes the test? All right, let's look at a new one. What about this one? So A, B, and C can be anything as long as they're even. What do we think? Go ahead. No, how come? Okay. So let's say you just said that A was 2. And if I multiply this by a half, I get 1, 0, 0. Why is that a problem? 1, 0, 0 is not inside S, right? So 1, 0, 0 is not in S. So the answer is no. So it's not closed under multiplication. So because of that, we can already say no, right? But can we check for closure under addition? What if I add any of these vectors together that have all even components? It's still even, right? So what happens when I add even numbers together? I'll get something even back. So what does it mean for a number to be even? Just making sure we know. Divisible by 2, right? So another way I could write A, B, and C is 2x, 2y, 2z. And if I add that to, I don't know, 2j, 2k, 2l. So these are just the most just generic even numbers. Then I'll get 2x plus 2j. Is that even? Mm-hmm. Yep. Because I can factor out a 2. Actually, just go ahead and do it now. Is x plus j an integer? Maybe I didn't make this clear enough. Is x an integer? Is j an integer? So is there sum an integer? Right. So we may not have ever thought about it before, but integers are closed under addition. Integers are also closed under multiplication. It's impossible to it's impossible to multiply integers together and get a fraction back. So this one's not a subspace, even though it meets closure under addition. It fails closure under multiplication. Questions there? Right. What about if they're odd? What about if A, B, and C are odd? Okay, so if I add, so you're saying this is not even closed under addition? All right, give me an example of something that fails it. Right, so 1, 0, 0 plus 1, 0, 0. So those two vector, or that vector that I wrote down twice, that's in S, right? And that adds together to give me 2, 0, 0. Is that an S? No. So not closed under addition. So is this subspace? Nope. Do we think it's closed under multiplication? Why not? What's that? Okay, I'll stick with 1, 0, 0 again. And if you said if I multiply it by 2, I get, what's that? Not. So if we look back at the conditions we set, what's my condition on R? It's a real number. I have literally no restrictions on it. So the fact that I can, 2 is real. So the fact that I can double one of these vectors and get out of S, so not closed under multiplication. So fails both conditions. No, not that, Mark. X. How are we doing? One thing that hasn't really come up, so I'll go revisit here. So the 0 vector had to be in this subspace, right? Is the 0 vector in this subspace or in this set? It's not a subspace. You sure? Is 0 even? Yeah. What's 0 divisible by 2? 0 is an integer. Feels weird to say that, but absolutely true. 0 is even. Yeah, that was my next question. The 0 vector is not in this. So the 0 vector cannot be in this because 0 is even. So there's kind of a hidden connection or a hidden condition with the subspace test. Every subspace has to contain the 0 vector. Every single subspace has to contain the 0 vector. So let's go back to the very first one, or actually, I have not shown you a subspace yet that wasn't just the trivial one. So let me hold that thought for now. So a couple ways to look at this. If I give you a set of vectors where the 0 vector cannot be, you're done looking. You already know that can't be a subspace. Or if you know you're looking at a subspace, you know the 0 vector is part of it. Every vector space and subspace contains. So I mean that condition's kind of it's not really a third condition, but it's an easy thing to look for. So what about this thing? So basically A, B, and C fit the Pythagorean theorem. So what should we check for? Is the 0 vector part of this? I don't know. Let's look at it. What would it mean if 0, 0, 0 was in this space?
be 0 squared plus 0 squared.
That would mean this would have to be true, right? Okay, I got the 0 vector. I think this is more difficult. Can we take like what kinds of things? Give me an example of something that's in here. Go ahead. Or do you have something else? Yeah, go for it. 111 is 111 in this space. Don't think so. But can we change this to something that is? Almost. 1 square root of 2. How about something a little friendlier? 3, 4, 5. How about 5, 12, 13? So there's some of these Pythagorean like triples that come out to whole numbers. So there now we've written 4 things that all live in this space. If I multiply any of them by a number, will I stay here? Will I stay in this space? Let's try it. What if I multiply 3, 4, 5 by 10? Then I get what? 30, 40, 50. Does that still fit the Pythagorean theorem? 30 squared plus 40 squared. What's 30 squared? 900? 40 squared is 1600, which is 2500, which is 50 squared. So I'm going to go ahead and promise you that multiplying any of the, actually, I don't have to promise you. What if I just multiply this by k? Then I get 5k squared plus 12k squared. That gives me 25k squared plus 144k squared equals 169k squared. What's the square root of that? Something k. What's the square root of 169? 13. So I can scale any of those and just get back k times the vector I scaled. So I believe it's closed under multiplication. It has the 0 vector in it. And the 0 vector really is a consequence of the scalar multiplication. Is 0 a real number? It is. So I should be able to multiply 0 by any vector inside that set and get something that's still in there. That's always going to be the same 0 vector. Now, addition. If I add things in here together, will I still be in the set? Yeah, so I'm checking for closure under addition. So I've written 4 examples here of things that are in this set, or actually 5 or 6, depending on how you want to look at it. If it's possible to add any 2 of those together and get something that doesn't fit this condition, then I don't have a subspace. Go ahead. Three, 4, 5 plus 5, 12, 13. And I get 8, 16, 18, which you're saying does not meet my Pythagorean theorem. So 8 squared plus 16 squared. What is 16 squared? 256, I think. So is that 320? Can't remember what 18 squared is, but I'm sure it's not 320. It has to be something that ends in 4.
324.
324? Okay. So the answer is no. It is not closed under addition. So it meets it meets the zero vector condition and the multiplication condition, but that's it. How we doing? Go ahead. Absolutely. Oh, that's not, so that subscript does not represent a power. Yeah. So in that case, we do not take negative numbers because so that subscript is how many entries the vector has. So because of that, we only take 1 and greater. So yeah, real numbers can be anything. But if you're talking about like this, the order of a vector, that has to be a positive integer. Good question. All right, so what about this thing? What does this say, first of all? Or like what kinds of things live inside this space? Go ahead. Right. So basically I can choose any real number and then the second coordinate will be doubled, third coordinate will be tripled. So I mean 1, 2, 3 is an example, right? All right. So how can we verify whether or not it's a subspace? Go ahead. Okay. So let's just treat it, leave it as arbitrary. And here's what I'll do. I'll say I'll leave one like this. I'll add it to something else of the same form, but with a different name. So first of all, do you agree that y2, y3, y is in this space? So even though I'm calling that variable something different, I'm still doubling it and tripling it and scaling the components like that. If I add these together, what do I get? X plus y, 2x plus 2y, 3x plus 3y. Or you can maybe rewrite this way. Does that tell us anything? So knowing that if we add any, like, that's about as generic as we can get. We added 2 generic things from this space together, and their generic result looks like this. What does that suggest to us? So is the thing we got inside our space as well? Only if x plus y is real. Is it? It is. The real numbers are closed under pretty much anything. Certainly addition. So since x plus y is real, then I still have this relationship. The first coordinate is a real number. The second coordinate is double that real number. The third coordinate is triple that real number. I have closure under addition. So addition is good. What else can we look for? Multiplication. And let's try to keep it as generic as possible. I'm just going to multiply. Basically, I know all my vectors inside S look like this. So I should be able to multiply any one of them by K and get something like this, KX, 2KX, 3kx. Is that inside S? That should be inside S because if X is real, then K times X is also real. So I multiplied it by a constant and I got 1 times a real number, 2 times a real number, 3 times a real number. So I have closure under multiplication. So really we're done. We have those two conditions, which means that is the subspace test. It's just those two. The fact that the zero vector, like the third kind of like hidden condition with the zero vector, that really is a consequence of these two. So because you already told me these two conditions are met, the zero vector better be in here. Is it? If X is equal to 0, I think I get it, right? But I've said this a couple times that if you have a subspace, then the zero vector better be in it. So 1, 2, 3 is a vector in this space, right? What's the thing I can add to it to get the zero vector?
-1.
Is -1, -2, and -3 in S? Should be, right? I can just make X -1 and I get that vector. And then what's the constant? What's the real number I can multiply by? Yeah. That's probably the more clear way to get the zero vector out of those conditions. If your real number can be 0, then basically you can scale any vector down to the zero vector. We doing okay with this? Good, because that was it. Right. So let's move on. Let's do some more stuff with that. Yes. All right, section 2. I'm going to talk about some things called spanning sets and the idea of, I think I've used the term linear independence, or I've called things linearly independent before. But I'm sure I have not gone into like real formal detail what that means. So let's talk about that. So now we're going to kind of go the opposite way. So in that first section, great. This is the thing they told me to do if it stopped working.